And again, I appreciate you guys taking a crack at the homework, doing what we're doing. And this is kind of what it looks like up to speed. I think up to the minute. There comes Frank. Okay, we got like what do we want to do with Frank? Let's see. Oh, I know I'll put this in green. Special color. I put Frank's in purple. Frank, you there?
Yep.
I put you in purple because it was 0.5 minutes before class. I love it. I love it. Sometimes the week gets away, right?
Yep.
All of us. It's like, oh man. I'm not gonna lie. I mean, I kind of reviewed my slides this morning. So I'm not much better, but this is probably like the fifth, I don't know, 10th time I've done this. So maybe got a review.
Yeah, I was
Anyway,
gonna Friday and then it worked out. Then I lost track of time today. So
yeah. All right, let's go on. Oh, here comes Lexi. All right. All right. I think we got everybody today. Except, yeah, Brent's on. I think I'm just, how about Scotty? Scotty's watching recording probably, right? Scotty Secor.
I'm here.
You are? Oh, you were Brent. Good. Oh, nice. Nice. All right, here we go. So let's go through the homework real quick. I didn't do all of them, but there were some, usually I pick one or two, but these are pretty good, So I'll start off with Dan. I like this one, Dan, because it's kind of a real world process. I mean, they all are, but this one happens to be at Barron Labs. So you take us through it real quickly.
Yeah, sure. So this is total settleable solids, which is a test we do specifically for, well, in this case, I'm doing King Industries when they bring in their quarterly or semi-quarterly wastewater samples that need to be, aligned with their permit requirements and stuff. So in terms of just the process portion, I kind of just outline step by step exactly what I do specifically to get the what we use for this sampling for the test. What we use the crucibles cleaned and getting the standards, weighing them out, the crucibles out, measuring out the specified volumes and such, and then ending with writing up the report, and that gets sent to the customer. In terms of like the inputs, it's just having all the factors that go into making sure the test is performed properly. So having correct amount of crucibles ready, the filters that actually house the samples once they are filtered, and that's what's being analyzed and reported. So making sure having to have properly sized and clean filters, making sure all the standards are in order, not expired, and ensuring all of the lab equipment like the oven and the balancer functioning. And then in terms of the suppliers, you mentioned that suppliers could also mean not just where we buy like things from, but also could be within the company and as to when things get handed to other people. So in terms of our purchasing department is who handles the orders that are given to them to purchase our standards and other things we need for testing. And the way our report system works is someone will write up the report. That report then gets checked by the manager, and then a final check is done with Kevin, with the director. So I added them as suppliers as well, since they are in the process and receive the reports. And then, the overall, the output is the overall goal of the test is calculating the TSS value, and then this will go into a scientific report with other tests as well. And then the customer that will receive the report would be King. So this is kind of just it was kind of helpful to break it up like this, and you kind of forget how many people's different departments actually all work hand in hand for just a simple test like this.
Yeah, I just love it. Here's why I love it. Like for example, everybody I hope started with process, right? And you work back to inputs. And I like this because, like, let's say it says acquire non-expired standards. So let's say it gets to the point where when I go find standards and I have to search for non-expired standard and it takes me half an hour, right? It's probably not going to happen, in the near future, but those are the types of things like the value of the mapping process, whether it's value stream mapping, whether it's a swim lane maps, or SIPOC. It's a high level view, but particularly when it's done with a group of people that are doing the process. But I love the way it's spelled out the actual steps. And then, we had some, Michael did painting the house, very similar, right? All the steps from removing furniture and boxes, and I gotta have them at my house one of these days. So I got a couple of rooms. And then the inputs, and then suppliers, same exact way. Again, this is like most of the tools that we're going to talk about they're best done, in 3 to 5 person teams, because it helps you really see things that we kind of just usually graze over. And here, I love the outputs on this one too. Walls are painted, they're hole free, the floor's paint free, Michael is paint free, the whole 9 yards. And then making iced coffee. This is AJ. I love this one too. And I think I've seen this one before. Because again, you go through it and you say, all right, wow, pretty good detail here. It's very simple processes, right? And then I think Alex, you did the rolling mill process too. Take us through that one real quick.
Yeah, no problem. So yeah, I kept it pretty basic for this. Just kind of went through kind of the overarching major things. So just going through the process. First thing the operator is going to do is go out and find their coil in their queue, whether it's in their immediate area or if they got to go out and find it. Load the coil into the machine, make machine adjustments, adjust the tooling, start running the mill, stop to change tooling between passes if needed, then get going again, continue running. Once they're done with the coil, they'll take measurements to confirm it and then unload the coil. So yeah, the inputs are the metal coil and then the tooling, whether that's work rolls or wipers or paper. Our outputs are the metal coil and worn tooling that now needs to go back to our grinding room. Suppliers being our vendors for the metal, the previous operation, whether that's coming from an annealing furnace or just coming into the factory now, and then the grinding for the work rolls, and then Veritiv being our supplier for the paper and stuff like that.
And, and I think again, if you could take measurements, you could have quality as a supplier, so they'd be involved in the process, the inputs. Yep. Yeah, like so. In other words, the more people you have on a team, the more visibility you give to the process. Well done. Yeah. Well done, everyone. Really good job, guys. I just wanted you to get comfortable. Just try it. It's like nothing crazy. And then we have our overachiever from Colorado. Desiree, you take us through this. This is a beautiful swim lane map of a dentist appointment.
Sure. So it starts with the patient coming to the dental appointment on time. A hygienist brings you back to the exam room, takes x-rays, gets you prepped for the dentist. The dentist comes in to give the dental exam, and tells the hygienist any issues. And then the hygienist will note any issues in your chart and determine if a second appointment is needed. If not, patient leaves the dentist. If yes, you set up a new appointment with the receptionist and then leave the dentist.
Simple as that, right? It's a piece that's beautiful. What I love it. One of my favorite lean practitioners, as you guys may know, is Sammy Bari, the dentist. Because largely we talked about last week, when we have a lot of handoffs, like when you do one for, say, you pick a process in your company, right? And you got a ton of handoffs. Every handoff represents usually hours or even sometimes days. In this case, it's it's a difference between, you know, an appointment that lasts, because the value added work here is getting my x-rays done really, right? I guess the exam kind of, but eliminating all the waste of waiting. So, you know, when we make improvements after doing a map like this, we're just looking at the handoffs and how long they take. And then you say, well, why do we have to hand that off to someone else? Really well done. I love it. I love the fact, and you also, Desiree, for everybody's information, also did did a SIPOC also. So she gets the extra credit. I'm not sure what it's gonna be. You know, maybe some points on the exam or something. But everybody's gonna pass the exam anyway, it doesn't really matter. So well done. Thank you, Desiree. Appreciate it. Appreciate everybody's doing your giving this a crack. All right. I think we had enough enough of me blabbing on PowerPoint, right? So we're gonna get into some descriptive statistics today. You know, so I think it might bring back some memories for some of you guys. You know, you maybe you've already done it in the past, or you use Excel all the time. For those of you that are in Excel all the time, I apologize. It might be a little bit of a review for you. But one of the processes that we're going to continue to look at over over the next bunch of weeks is because I think it's an easy real life example is my weight. And we're also going to look at my blood pressure. And what I do is I sample my health process, my health once a week on Fridays. You know, I weigh myself and I do a blood pressure. And I've been doing that since January 2006. As you may know, I referee college football, and the last thing that they will tolerate is an overweight official, you know, at the Division I college level. You know, so you know, also there's a bit of history of heart problems and you know, my father, and so I realized as I was approaching 5'9" on a good day, close to 200 pounds, I better start collecting data. So what I have here, guys, is 775 weeks worth of weight data. And the theme today, when we talk about descriptive statistics and when we get into the PowerPoint, I like to do this first, the math practice first, then go to the PowerPoint, because I think you won't glaze over as hard, I don't think. But the purpose is simple. How do we make data talk? Not only talk, but scream at us. Because data, unfortunately, just lays on the page, nice and quiet, right? We want it to scream at us what's happening. And there's a couple things that we're going to be looking at. One is descriptive statistics, which are things like this, where it's a long list of data, and we're going to kind of take a look at it in a few different ways, right? To see what kind of conclusions we might draw from it. And then there's inferential statistics, which is where we start getting into things like hypothesis testing, predicting from data that we get. All right. So what I'm going to go through with you guys is actually going to be the homework, but I'm going to erase everything and send it to you just like this, blank. And I'm going to ask you to go ahead and do the home, you know, and practice these. So again, I apologize if, you know, if it's simple, if you're using Excel all the time, and you guys do, you know, probably, you know, the engineers we have here, but you know, not everybody works in Excel all the time. You know, so just let me take you through it. So here's, again, I could probably look at the data, but there's 775, I think, pieces of data here. So I may not know. I may have to go through if I want to know what the maximum, what's the most weight that I gained, you know, that I weighed. I'd have to go through 775. This could be 10,000 pieces of data, right? This could be 1,000. It could be 100. It doesn't really matter. It's all the same, right? Because this Excel makes it so easy. So the maximum, like all functions in Excel, are press the equal sign and then hit whatever I want. Like just start typing max. And there's max. Double click on it. And then I'm going to highlight all my weights. And it's going to come back with 199 pounds is the most that I weighed in the last 770 weeks. All right. Same thing with minimum. Type equals, start typing min, double click on min, highlight weight. And the least I weighed, I was close a couple weeks ago with 175 pounds. So I started fasting, by the way. So hopefully I'm seeing the numbers start to drop. And then the range is what's the biggest number minus the smallest number, right? And the range of weight is, so I'll go equals 199 minus, a little minus the dash, 175, 24 pounds. That's what the range has been over the last 775 measurements. And the mean is another word for the average. What's my average weight? Equals av. And then I click on average and highlight the whole thing. And my average weight, 184.4 pounds. What do you think the mode is? Anyone?
The most common.
Yep. Good job, Frank. Oh, equals mode. Double click. Most common weight, 186. That's the number that occurred, the weight that occurred most often over the last 75 weeks. And the median, anybody except Frank?
The number in the middle.
Exactly.
you
And it
organize them
differs
from
from
highest
the
to
mean,
lowest.
right? It's the exact middle of my sample. Keep in mind that these are just samples, right? I'm not, my weight is something that changes from, I mean, it depends on how you measure it, but it could be hour to hour, minute to minute, right? So I'm basically sampling. This is a sample of my weight that we're looking at here. So the median number on my sample, again, median, double click. And 184 pounds, very, very close to my mean. All right. And then standard deviation, all that is a measure. What's the average amount of weight week to week that from my mean, from the average? So my average is 184. How much variation is in my process? All right, of my weight. So when I go standard deviation, and you're going to get, all I did is type ST, and you'll see deviation population or deviation sample. And I'm going to pick sample because that's all I'm doing here, right? I'm only weighing myself once a week. So I'm taking a sample of this, particular process. And then it asks me, same thing, just highlight my weights. And I could see that the standard deviation is 4.18. What's the units? Anyone? What are the units for standard deviation there?
Bill, would it be pounds? Would it be pounds in this
Exactly,
case?
Michael. It'd be pounds, right? That's 4.2 pounds. So that's the average amount of variation from that 184, right? So Six Sigma is nothing more than trying to eliminate variation. So I want to make that 4.1. I think last year or last time I did this class, it was 4.8. So, I mean, I'm getting better, right? Or 4.7 pounds, I think. But the idea is to constantly squeeze that standard deviation. Make sense? And then variance I put in here because basically all variance is the standard deviation squared. And the reason we do it is because, as you'll see as we go on, a lot of formulas call for variance and not standard deviation. And all it is so equals var. And again, you'll see VAR sample and variation population. I'm going to take sample. And I'm going to highlight my weight. And it's going to be my standard deviation squared, or 4.2 times 4.2. And that's where I get 17.48 pounds. And again, the reason it's important is because as we go on, there's some formulas that you'll see as we go forward, that call for variance and not standard deviation. Now, the next thing I want to do, if I just graph this thing, What I want to do is I want to do something. I want to find out if this is a bell-shaped curve. And a bell-shaped curve means that my process is in control pretty much. And I'll show you what I mean by that. So in order to do that, I have to take the mean and the standard deviation. I'm sorry, I have to take each weight, all 700, all 700 weighings, 750 weighings, and compare it to the mean and the standard deviation. And the way we do that is we hit equals and then norm. And the first one that pops up is normal distribution, norm dist. And when I click on it, it's telling me what to do down here. You see this little balloon down here? So the first thing it's asking me for is X. So the X I'm going to pick here is my weight. Just pick the first one, 194, comma. And then I'm going to pick the mean, comma. And then you see how it highlights the standard deviation now? I'm going to take the standard deviation, comma. And then it's going to ask me if it's a cumulative distribution. And the answer to this one is false. It's a probability mass function. We'll get into that in the next few weeks. But just when you do the homework, just press false. And then what I have to do is I have to go back into the formula and take my mean, which is G2. And I got to put a $sign on both sides of the G. Like this. I'll explain why. And I have to do the same thing. Maybe you guys know why already. Probably explain to me. I insert those $signs. Any idea why I put the $signs in for the mean and the standard deviation?
Lock those values in.
Yep, bingo. Because when I go drag this down, it's going to try to take G3, G4, and it's not going to, the formula is not going to work, obviously. Thank you, Frank. I hit enter, and there's my Z distribution for that data point. And all it's doing is taking that 194 and doing a mathematical, equation with the mean and the standard deviation. And then I take this and you double click it, but I don't know, today my practice this morning, it didn't do it either. So I'm just dragging it all the way down. I apologize. Down to the last piece of data. And there it is. There's all set. Now, what the hell good was that, right? What kind of exercise is that? So I'll tell you why it's important. If I take the date and the weight, and I go to insert a recommended chart, I have an option of a scatter diagram, which is what you're looking at here. And it kind of gives me a sense of where the data's been, where it's been the longest. And it's basically comparing weight and time. Or I can do a line diagram, which again is just one piece of data after, like a line chart, right? So there's a whole bunch of things we can do like that. But what I'm interested in is I want to know if my process is a bell-shaped curve. Is it normalized? Is it a normal curve? So to do that, I take date, the weight, and the Z distribution that I just so carefully calculated with a few mouse clicks. I hit insert, recommended charts, and voila. I have a pretty good bell-shaped curve here. I just want to point a few things out on this curve. One is you can see where the mean is here, right? It's at like where the top of the bell is, 184.4. You can see that my mode is right at 186. And my median is right where pretty much where my mean is. So what that tells us is this is pretty much an ideal, almost an ideal bell-shaped curve, because it's called a Z distribution, where the mean, the mode, and the median are almost the same. So we're getting pretty close. All right. So if you make 184 the mean 0, let's pretend it's the number 0. I could plot this exactly the same way, except have to the right 1, 2, or 3 standard deviations, which would be one deviation would be 4 pounds. So it'd be 0, 4 pounds, 8 pounds, and the same thing to the left. So 6 sigma means all of my data points are 6 standard deviations under that curve. 3 to the left of the median of the mean, the average, and 3 to the right. And the game again is to constantly squeeze variation out of this process. All right. Let me see anything else I wanted to cover. We're going to talk too about something called central limit theorem today. And all it simply means is if I don't get a bell-shaped curve, it means a couple things. It means my process isn't in control. It also means I may have to go and collect more data. And I'll give you an example of that. So we talked last week about if I wanted to find out the average weight of killer whales. Obviously, there's not enough money, or not enough time to go out and catch every whale and weigh it. So I have to do a sample. But the problem is, let's say I decide I'm gonna catch 20 whales, weigh them, and then put them back safely in the water. I might get 10 of them that just got done eating, right? They just had a huge meal. Then I might get 5 of them that are close to dying and they're losing weight, or they might be small, young or whatever. And the thing is, I'm going to get the average weight the more data that I collect, the more whales that I can collect. So central limit theorem means if I don't have a bell-shaped curve, go get more data. All right. And that's assuming my process is under control. So my weight is, I think it's pretty much in control. And again, my objective now is to shift it towards the 170 to 185 and there still be bell-shaped, but with not a lot of variation week to week. And think about all your life processes that go into weight, right? How many calories, how much sleeping you do. There's a whole bunch of factors that go into this one data point that I've been taking. All right. So any questions, guys? This is the homework. All I'm going to do is ask you to do exactly what I just did. I'm going to send you the data set and just go through the exercise of, and for those of you guys that do Excel all the time, it'll just be a few minutes. And if you have any questions now, guys? We're good. All the stuff that we just did too over the next couple of weeks, I'm going to save it for next week or the week after, actually for next week. But basically I can do everything I just did with like 3 mouse clicks. But I didn't want to spoil the fun of going through, because basically we can go through each formula too, and look at the formula. You're going to see the formula for variance and standard deviation when we get to the PowerPoint. And with Excel, you just don't need, it's good to know, but you don't really need to do it. Everybody cool with that? Clear? Not crazy, right? Just fun with math.
No, it's a good refresher. Looking forward to it.
Thank you, Michael. And now we go into the PowerPoint is going to be wicked easy and fast. So far, welcome to measure 2 out of 3. So we got one more week of the measure. Today we're doing all the light blue. Last week we did process mapping, SciPoc, kind of did an flyover of VSM, XY, basic statistics, different kind of counting methods, things like that, and data collection. And today we're going to go through what we just did: descriptive statistics, central tendency and dispersion, distribution and normality, central limit theorem, and then look at a couple of different types of graphs. So let me make it. There we go. And then next week, we're going to do MSA, pretty much. Precision accuracy, bias linearity and stability, gauge R&R, all that fun stuff. Today, I think it's more fun, but So descriptive statistics. And again, as I mentioned, what descriptive statistics are they're describing what's going on. They're enumerative, they're countable, right? Statistics. Although they're things that we're measuring, right? But we can count how much data we have. It includes organizing, summarizing, presenting it, and there's a whole bunch of ways to make data talk. Histograms, pie charts, box plots, etc. Along with, the things that we're looking at in terms of mean, mode, median, all that stuff. And then inferential statistics, which we're going to ad nauseum, hypothesis testing. It includes predicting and drawing conclusions, because once my process is stable, then I can start to make predictions about future performance, right? Until I get the process stable, I can't really do much in the way of predicting. So descriptive statistics, the main features of the collection of data, the shape, location, and the spread. Those are the three things we're going to talk about. It's a presentation of data collected, and it does not provide inferences like hypothesis testing would. We're not trying to infer anything. All we're trying to say is, right, what's it telling us as is? So location is the mean, the median, and the mode. It describes the value where the data tend to cluster. And there's the formula for the mean. Everybody knows how to do an average. We add up all our values, divide it by the number of values, and we come up with a number. Or you could just say equals mean, and then click on our data, and it tells us. And the median is the middle value. It separates the finite set of data into two parts, one with values higher, one with values lower. The mode occurs most often. If no number is repeated, there's no mode for the data set. And descriptive statistics, that's the spread. And that's kind of when we got into range, variance, and standard deviation. So that's how much is the data spread, my weight data. The range is the numeric difference between the greatest and smallest value. The variance measures how far on average the data spread from the mean, from the average. And there's the formula. There's my sample size, which is number of -1. So it's the sum of all my data squared. And standard deviation, which is we use most of the time, as in this class, how far the same exact thing. It tells us how far they are from the mean. It's the square root of the variance. And all data points are accounted for in calculating it. Variation is variance away from a target value increases the chance of a product, service, etc. being rejected or not purchased. Variation is the enemy of any quality process. And we're going to get into different types of variation, common causes, special causes as we keep going, but that's the definition of variation. And again, keep in mind, this is something we're going to continue to come back to is, Six Sigma, when you're looking at where Six Sigma is 99.997% yield, 3.4 defects per million opportunities. There's a defect rate all the way down to 1 sigma. And we covered this back in the define phase. Distribution and normality. This is the bell-shaped curve that we so nicely demonstrated today. I thought anyway. It's a probability distribution of a continuous random variable whose values spread around the mean. So again, values in a normal distribution, the values are spread symmetrically about the mean. That's why I get a bell shape to it, right? It can completely describe by using its mean or variance. And that's what we did with that formula, right? Equals norm. And it's a bell shape. And the Z distribution is kind of what we have for my weight. It's the simplest normal distribution where the mean is equal to 0 and the variance is equal to 1. Or if you think about it, the standard deviation as we move right and left, each one of these lines represents one standard deviation. All right, so 6 sigma would be no more than 3 standard deviations to the right of the mean, and no more than 3 to the left of the mean. And then there's a little bit of location. You kind of see it on my weight too, where I could be skewed left or right. But a normal distribution, a Z distribution, is the mean and the median, the mode are all the same. And you remember I think it was the median was a little off, like it was 185 or 186, and you could kind of see it skewed one way or the other. But again, as the process becomes more and more in control, it'll more resemble the graph on the left, where the mean, the median, the mode are all the same. And the cool thing about a bell-shaped curve is that the percentages that I'm giving you here, they hold true once I get to a normal distribution. Once my process is in control, then I know that 68% of my data is in between 1 and minus, within 1 standard deviation of the mean, plus or minus. And 95% of my data is within 2 standard deviations of the mean, left and right, plus and minus. And 99.7% of my data, of those 775 data points, is within 3 standard deviations to the right and left of my mean. And I'll give you an example of why that's important. The predictability. I think I have an example I want to show you. Yeah, so basically, this slide, all it's saying is, yeah, if it's 68% within 1 standard deviation of my mean, then on each side of the curve, it's 34% and 34%, 13.5, 13.5. And it allows us to do things like this. So let's say I have a physics class with 800 students. And the test scores are normally distributed with a mean of 75. So the average for the class of the 800 students on this test was 75. And there's a standard deviation of 7 points. And so the first thing I'll do is take the mean. I know it's normally distributed, so I can do a bell-shaped curve. And each vertical line is going to be my standard deviation of 7. And keep in mind that 7 points is the average deviation from the average of 75. So I just set up my line in both directions. 75 is my mean, 82, 75 plus 7 is 82. That's my standard deviation. Plus 7 is 89, plus 7 is 96. And same thing the other way, 75 minus 7, minus 7, and minus 7, okay? But now I can answer some questions. I can make this data talk a little bit. One, question A, anybody that wants to pipe in, if you have like your phone handy or whatever, what percentage of the class has a test score between 68 and 82? Anyone? Approximately?
%68.
Yep, you got it. 68%. Simple. So 68% have a test score between 68 and 82. Approximately how many students have a test score between 61 and 89? Well, just to add up all my percentages, multiply it times 800, right? I won't have you do it. What's the probability that a student chosen at random has a test score between 54 and 75? What's the probability that a student chosen at random has a test score between 54 and 75? Like, add up those percentages, multiply times 100, 800, and that's the probability. And how many test students have a test score greater than or equal to 96? And then you can see that the tail, the tails are on both ends. 0.135% times 800, or 800 times 0.135, give me the number of students with a test score greater than or equal 96. But that's the beauty of the bell-shaped curve. I can even look at my process, even it's starting to scream at me. Like, in other words, what was the process of this test? How did I do as a teacher? And why assess normality? Because we're going to see a whole bunch of different types of distributions, and not all processes have a normal distribution. And you'll see as we go, like especially when we talk about discrete data, which is stuff we count, versus measure. For example, one cannot have a phone call shorter than 0 seconds. Like, in other words, for measuring the time on, for a service call, something like that. But normality, the reason we assess it, and I'm going to show you how to do it a bunch of different ways over the next couple of weeks. It's so important because it allows us to predict. And the normality testing, I think it's the homework 2 weeks from now, where you can run a normality test. And basically we're looking at, can I draw a nice straight line through my data? And we're going to get into p-value and alpha in a couple of weeks. Central limit theorem, sample size increases, data gets closer to a normal distribution. Just think of the whales, right? And getting, trying to get a bell-shaped curve, the weight of killer whales. And generally, sample size threshold is when n is greater than 30. I mean, I just saw we did 775 samples on my weight, but we don't really want to start talking about a process until we're over 30. Which is good news for all the Ulbrich people, because you guys got data like crazy, data sets. You guys are using it well. Graphical analysis, really simple. I'm going to show you one that you might not have seen before. Maybe you have. It's to visualize all that data. Like the bell-shaped curve is a great example. The scatter diagram is a good example. There's some examples of some graphical analysis tools: box plot, histogram, scatter plot, run chart, which is, we're going to get into control. When we get into the control phase, we do a lot of run charts, and then the dot plot. A box plot, this is the one you may not have seen. It's also called a like a whisker diagram. Have anybody seen this before? I'm going to go through it real quick, just in case anybody ever asks you, if you're at a party or something, and someone says, hey, you ever done a box plot? You can say, I think I know what it is. Basically, you're taking everything and putting it into percentiles. And I think I'm going to skip this slide and go to the next one, because I think this makes it easier. So if I want to do a whisker plot for this set of data, so the data is the numbers on top, 11, 22, 20, 14, 29, 8, 35, etc., right? First thing I do is I take them and put them in ascending order, starting with my min 8 and going all the way up to 49, which is my max. So on the bottom here, you see I did another line going from 0 to 50, which encompasses all of my data set. The first thing I'm going to do a box plot is I'm going to plot my median. So we're talking about medians here, right? So the median here of the whole data set is 20. And I'm going to draw a line, another line with a couple of whiskers. That's why they call it a whisker, a box and whisker plot. My median goes on, and I label it Q2. And all it means is that's the median of my whole data set. Now I'm going to take all the data from my median to my max and find the median of that data. So from 20 to 49, and that happens to be 28. I'm going to draw another vertical line right at 28. And I'm going to do the same thing with the data to the left or lower than my median, which is going to be from the number 8 to 20. And that's going to be a median of 12. So I'm basically breaking up my data into basically three sets. And then I just draw a box around those vertical lines. And what do you think this tells me? So I'm looking at, here's a data set. There's my min at 8. There's my max at 49. This is what my box plot is. It's somewhere here. What does that tell me? At a glance.
Your data is skewed to the low end of the range.
Exactly. And this is such a simple example, Frank, But it could be very, very helpful for my weight, for example. In other words, where's most of my data? Is it that 199 range, the 189 to 199 range, or so it gives us a feel for the location of our data. It might be one you haven't seen before. And these are the ones that you have, probably histograms, scatter diagrams, just one click away on Excel. You saw that with the weight. A run chart. Again, we're going to get into control charts ad nauseum in the control phase. And dot plots, if you want to see the frequency of individual values. And that's it. Order of. Whew, record.
Hey, Bill, question on that, that diagram you showed an example of, have you used something like that in a practical sense? And
The
what would
whisker?
be of where, yeah, the one you were just talking about a few minutes ago. And
I have
what would
not
be-
done. I have not. I'll be honest
No.
with you. I haven't done it in a practical sense. I've done it a lot of different ways teaching it, though. That doesn't count, though, right, Frank?
I mean, this seems like something you could draw up on a piece of paper pretty quickly and get
Absolutely.
rather than
Absolutely.
having, if you don't have your computer available to analyze it right in a spreadsheet format.
I mean, I think the useful part of it would be, if I'm collecting data for a long time and I see where the data lives, like, what the location is, I may change my specs, for example. I may make an adjustment in my specifications, something like that, or pass fail, or. Good question, though. But no, the answer is no for me. Has anybody seen that before? The box and whisker? Is that new for you guys?
Definitely back in college, not a
Probably,
long
right?
time now.
All right, so that's class. I'll send you recording. I'll send you the math practice updated, with the blanks, and just have some fun with it. Go through it. If you have any questions, give me a holler. Next week, Tuesday at 3, okay with you guys? Because I think Monday I got like 50 people coming to this house. What do you think?
Yeah,
Is
I'm
Tuesday
gonna-
all right, guys?
I got the
It's
day
fine
off.
for me.
What's
I'm
that?
out that whole week, so
You're off, Desiree?
yeah, I'm out that whole week, so I'll watch the recording though.
Okay.
I'm out Tuesday as well, so that's fine with me.
Yeah, you were here anyway, so it's just a matter of, I think, you don't even have to watch the recording unless you get stuck on the homework a little bit. It might be nice to just go back and, and get the homework, help you with the homework. So if the homework's not up to date, don't sweat it, guys. I definitely don't get too far behind though. People are traveling, people are doing different things. Just try to get to me. I think it's important that, I feel like you're comfortable with some of the concepts and if I'm teaching it okay. So, all right. Love you guys. Have a great afternoon and have a great Memorial Day. If I don't talk to you, I probably talk to Michael before long and AJ and maybe the Holbrook people, but have a great
Thanks,
day.
Phil.
You guys.
Excellent.
Sounds
Have a
good.
great
Bill.
Monday.
Have a good week.